String theory's dream is a single, self-consistent mathematical framework that unifies gravity with quantum mechanics, and all fundamental forces with all matter. In 1968, Italian physicist Veneziano accidentally discovered a beautiful mathematical formula that perfectly describes the scattering amplitude of the strong interaction. Later, Nambu found that the physical meaning of this formula is, fundamental particles are not points but one-dimensional vibrating strings. Different vibration modes of strings correspond to different elementary particles, just like different vibrations of guitar strings produce different notes. From 1984 to 1985, the first superstring revolution erupted, and 5 consistent superstring theories were discovered. In 1995, Witten proposed M-theory, unifying all 5 string theories into a larger theoretical framework. String theory has been on its journey ever since. Today we discuss, after 58 years, how far has string theory come toward the ultimate goal of a theory of everything? String theory requires 10 spacetime dimensions, a mathematical requirement for theoretical consistency. We perceive 3 plus 1 dimensions, with the extra 6 dimensions compactified at extremely small scales, about 10 to the minus 33 meters. Think of a water pipe. From afar it looks like a 1D line, but up close it's a 2D tube. Extra dimensions are like this tube surface, just compactified extremely small. Strings come in 2 basic types, open strings and closed strings. Open strings have free ends and can attach to D-branes, transmitting electromagnetic, weak, and strong forces. Closed strings form loops and naturally contain a spin 2 particle called the graviton. This is the key to how string theory unifies gravity and quantum mechanics. Gravity is not forced in but is an inevitable result of closed string vibration. The 5 superstring theories are unified through M-theory, which lives in 11-dimensional spacetime. Although string theory hasn't been directly verified by experiment, it has achieved tremendous success in mathematics and theoretical physics. The first landmark achievement was Strominger and Vafa's work in 1996. They used D-brane configurations to precisely calculate the Beaconstein-Hawking entropy of extreme black holes, matching classical general relativity perfectly. This was the first quantitative success of quantum gravity. The second achievement was Mel Desaina's AD-SCFT duality in 1997. It states, a string theory with gravity in anti-de Sitter space is completely equivalent to a conformal field theory without gravity on the boundary. This revolutionized how we study quantum gravity. String theory's impact on mathematics is equally profound. Mirror symmetry connects algebraic geometry and symplectic geometry, earning Witten the Fields Medal. In cosmology, string theory also provides new perspectives, such as string gas cosmology and moduli inflation models. The landscape problem is the biggest theoretical crisis facing string theory. String theory requires extra dimensions to be compactified at extremely small scales, but there are countless choices for the compactification geometry. Each choice corresponds to different physical constants, different particle masses, different coupling constants, different cosmological constants. There are at least 10 to the 500 possible vacuum states. Our universe is just one of them. This creates a fundamental question: if string theory allows 10 to the 500 different universes and we can only observe one, how can string theory make unique predictions? Physicist Peter Woit sharply criticized, string theory is not wrong, it's not even wrong. If a theory can explain any possible universe, it actually explains nothing. This is a fundamental challenge to scientific methodology. The second challenge for string theory is background independence. In Newtonian mechanics, space and time are an eternal, unchanging stage on which matter moves. But in Einstein's general relativity, spacetime itself is dynamical. It bends, oscillates, and evolves. A true quantum gravity theory should inherit this principle: spacetime should emerge from the theory rather than being presupposed. But string theory's current formulation relies on a fixed background spacetime. Strings vibrate in a preset spacetime. This contradicts the spirit of general relativity. String field theory tries to solve this problem but hasn't fully succeeded. Critics from loop quantum gravity point out this is a fundamental defect of string theory. Supersymmetry is one of string theory's core assumptions. It says every elementary particle has a supersymmetric partner. Fermions have boson partners, bosons have fermion partners. In the early 2000s, physicists widely expected the Large Hadron Collider to discover supersymmetric partner particles. But the LHC has been running for over a decade, discovering the Higgs boson but finding no supersymmetric partners. The simplest supersymmetric models have been excluded above the TeV scale. This is a major setback for string theory. If supersymmetry doesn't exist at all, string theory needs fundamental modification. But there's another possibility: supersymmetry might appear at higher energy scales, just beyond our current accelerator's reach. This question remains unanswered. String theory faces a fourth and most fatal challenge: the testability crisis. The characteristic length of strings is the Planck length, about 10 to the minus 34 meters. The strongest particle accelerator, the LHC, can probe scales of about 10 to the minus 19 meters. The gap is 15 orders of magnitude, like trying to observe an atom with the naked eye. String theory's predictions are virtually impossible to test with any existing or foreseeable experimental technology. Possible test pathways include primordial gravitational wave signals in the cosmic microwave background, corrections to gravity laws from extra dimensions at microscopic scales, experimental tests of the black hole information paradox. But these are all indirect and uncertain. String theory supporters say string theory's predictions are too refined for current technology to test. Critics say if a theory can never be tested, it's not a scientific theory. The Swampland Program is one of the most important developments in string theory, proposed by Harvard's Kamran Vafa in 2005. The core idea is, not all apparently consistent quantum field theories are compatible with quantum gravity. Theories compatible with string theory belong to the landscape, incompatible ones belong to the swampland. The program's goal is to find swampland criteria, which theories are in principle incompatible with quantum gravity. Discovered swampland conjectures include: the weak gravity conjecture says gravity must be the weakest force, the distance conjecture says moving infinitely far in field space necessarily produces infinitely light particle towers, the DS conjecture says stable de Sitter vacuum may not exist. These conjectures dramatically reduce the 10 to the 500 possibilities. More crucially, the Swampland program restores testability to string theory. For example, BICEP2's erroneous data once contradicted swampland conjectures, showing the program is falsifiable science. The Bootstrap method is another important sign of string theory's renaissance. The traditional research path starts from string theory and derives its predictions. But Bootstrap asks the reverse: what kind of theory can be derived from the most fundamental physical principles? In 2024 to 2025, Chung, Reman and others achieved breakthrough progress. They assumed the universe still satisfies the basic principles of quantum mechanics in the ultraviolet region, especially supersoftness, a mathematical statement avoiding infinitesimally small distances. They found the only scattering amplitudes satisfying these conditions are the Veneziano amplitude and Virasoro-Shapiro amplitude, which are precisely string theory's core formulas. What does this mean? If assumptions X, Y, Z are true, then string theory must be true. The debate shifts from whether string theory is correct to whether these basic assumptions are correct. Latham Boyle commented, "I don't think the most likely conclusion is that string theory must be true. But these results do show string theory is very special." String theory's path to a theory of everything can be divided into 4 stages. The first stage is complete. The basic mathematical framework is established, with black hole entropy and ADS/CFT as landmark achievements. The second stage is underway. The Swampland program and Bootstrap method provide new testability, and background-independent formulations are being explored. The third stage is the biggest challenge: how to select our universe from 10 to the 500 possibilities. If supersymmetry doesn't exist, how does string theory need to be modified? Which predictions can be tested in current or future experiments? How to solve the cosmological constant problem? The fourth stage is the ultimate goal: a fully self-consistent quantum gravity theory, unifying all fundamental forces in all matter, explaining the values of all fundamental constants, explaining dark matter and dark energy. This may require 20 to 50 years of key progress, or even longer. String theory may be correct, but there's a long road to a theory of everything. Reasons for optimism: the Bootstrap method suggests string theory might be the only theory satisfying fundamental principles. The Swampland program is systematically narrowing possibilities, cosmological observations may provide definitive evidence in the next 10 to 20 years. Reasons for pessimism. String theory's predictions operate at scales too small for direct testing. The landscape problem makes unique predictions difficult. The non-discovery of supersymmetry undermines string theory's theoretical foundation. My judgment, string theory may be correct, but becoming a TOE still requires at least 20 to 50 years of key progress. The greatest hope comes from cosmological observations. Primordial gravitational waves and the cosmic microwave background may provide decisive evidence in the future. String theory has profoundly changed our understanding of the universe. Whether or not it's ultimately verified, the exploration itself is already written into the history of science. Thank you all.